Alright, so this is just for interest. I haven't put it up on the web because it's not really part of what I'm teaching you, but not everything that I teach you only has value if it's in a test. Okay, some things are just interesting or nice to clear up. Okay, but it's not, it's really for those of you who have programmed in Java before. So we started off last week saying, alright, so we program in this high-level language. How does it get converted into machine language, which is really what the CPU understands? Okay, and I said that there were two ways of doing it. And I used an analogy for both of them. Okay, for each of them. So, the first way is a compiler. An analogy I used was a book. Girl with the dragon tattoo. And the reason I use that analogy is because she's a computer programmer, sort of, she hacks. Okay. So that book was written in Swedish, and then someone came and converted the whole book into English and did a job that is similar to what a compiler does on a computer. A compiler will take an entire program written in a language and convert the whole thing into machine language. Which means that if you can install that compiled version on your computer, you don't need to have the compiler. You just have the machine language for your computer. So you can download an executable for Windows or Apple or Linux. You have to get the right one so it will run on your machine. Okay, but you can download that, and you don't need to have the compiler that originally converted that program, whatever it was in. You don't know what it was written in, into this executable. Okay, so that's what a compiler does. It takes the whole thing and does what someone who would be translating a book would do the whole thing at once. And you would never need to see the woman who translated The Girl with the Dragon Tattoo, which used to be called Men Who Hate Women in Swedish. But that's another thing. You don't need to ever see the compiler. So the analogy here, and it's an analogy, it's a story, it's not the answer, so please don't write about books in the test. Okay? But the analogy to help you understand it is that you don't ever have to see this person who translated that book. You just buy the book. So you can just download compiled programs which are in machine code for your machine off the web and run them on your computer. And you don't need to have this. Okay. It's a one-shot translation. The source code is read only once. Yes. Yeah, well, it's going to compile it for the specific hardware. So yes, it does care in the sense that it is only compiling to a certain machine code. So you would have to compile it on different machines, or with the compiler for different machines to get executables for Apple. And you know, Apple with the Intel chip, which is now very prevalent, will be different to the older version of all the hardware. It's a bit complicated. So what's the relationship between the hardware and the operating system? The operating system is a program that runs on your machine all the time and accepts and runs other programs. That operating system is specific for your machine as well, and your particular chip. But the compiled program has to interact with the operating system and the hardware for that machine. So it's fairly complicated. Because different operating systems will handle the hardware differently. Okay. But the whole, so what you need to get here is that there is a compiler, and that's one way of doing it, and it's one shot, and it just does it once off translation. Okay. Then you have an interpreter. Okay, so the compiler is a program itself. Huh? It's a program that translates other programs into machine language. The interpreter is a complex program that simulates a computer that understands the high-level language. So it's a program that has to be on your computer if you want to run that language. So Python is interpreted. So you have to have Python installed on your computer. Okay, which is why you have to install Python as well as Wing if you're wanting to run it on your computer. So you need to have this interpreter running. And when I do this, and I'm interacting here, I am running the interpreter in a terminal. Okay, I often like to do it this way. Okay, but I'm running the program. I can exit the program. Okay, and then it's just my usual terminal. Don't worry about it. And then I run Python 3, which is a program. So now I'm running the interpreter, and it interprets Python. So when I say something like print hello, it will interpret that and do what the instruction says. Okay. So the interpreter is a program, but you need to have it running on your computer. The analogy is a bit like the UN, and some discussions going on in French, and you have an interpreter with an earphone who translates it sentence by sentence. So it's interactive. As each sentence happens, the interpreter translates it. It doesn't look ahead. Okay? It doesn't do the whole speech at once. It waits. It's much more dynamic in that sense, that you can change your mind and do different things. Okay? You can just run it as a straight program, so that's how we usually do it. We write Python program, and we run it through an interpreter, and it just goes through each line. But it is actually going through each line, one at a time, and interpreting. Which means it can be slower, tends to be slower. Worst case, seriously slower than a compiled program. But it's much more dynamic and flexible, and easier to learn with. Okay. So, when you have an interpreter, you need the source code, the original program, and the interpreter every time you want to run your program. Whereas if you're using a compiled program, you need just that executable. However, it also means that if you have your source code Python and you move from Windows to Apple, make the upgrade, then your Python programs will work fine. You just have to install Python on your Mac. Okay, whereas all your executables from Windows will not work on your Mac. You'll have to get new executables for each of those programs. So you can see the advantages and disadvantages. Java is also interpreted, but also in a weird way compiled. So just so you're aware, it's also interpreted, but it's compiled to something called bytecode.
Is Delphi also similar?
I don't know. Actually, I don't know Delphi very well, to be honest. I'm used to know Pascal, which was compiled. Yeah, but I don't really know Delphi. I have a strong desire to. So, compiled programs tend to be faster, and interpreted programs tend to be more flexible, can be developed and run interactively. The biggest argument that people will use against Python is that it's slow. Okay? Because each line has to go through an interpreter and then be executed by the hardware. Okay, any questions about this? Yes?
What are compilers and interpreters written in?
Okay, so what is the compiler written in? Or the interpreter. When I say compiling, I mean compiler or interpreter. The language, the program that's doing the translation. What are they written in?
Machine language?
Machine language? The early ones were written in assembly, which is one step up from machine language. So the early compilers or interpreters were written in assembly language. Later, Pascal and C were popular choices for writing the compiler. All right. C Python is actually what you're using. We're calling it Python, but it's C Python. It's Python, and the interpreter is written in the C language. Okay, so the interpreter is a program. It was written in C, and it translates the Python into machine code. That is the most common implementation of Python. Okay. However, you also get compilers written in the language that they compile. Okay, so they're written, they could compile themselves. Because it's quite a nice, elegant, beautiful way of thinking about this. It's recursive. Okay, so the compiler is written in a language, the same language that it compiles. So these are called self-hosting. The very first self-hosting compiler, capable of compiling itself, was created for Lisp in MIT in 1962. And incidentally, I had lunch on Friday with someone who's working in PyPy. PyPy is Python interpreter that's written in Python. It currently runs on version 2.2.7, and if you're interested, you can go have a look at pypy.org. Okay. The advantage of PyPy is the same advantage that Python has, in that it's very powerfully expressive language. Okay. This is for interest, all right? These slides I'm not going to examine you on. They're for interest. The extension, and I hope to provide a little bit more depth for those of you who have programmed before, because I have quite a complex task that involves teaching both ends of the spectrum, and I try and make everyone happy, which has the danger that no one's happy. But really, if you aren't happy, you must ask a question, and then I'll start directing the lectures towards you. Yes?
Is PyPy the compiler or interpreter?
An interpreter, but it also compiles. So the problem with computing is you say there are this and this, but then there are all these hybrids in between. So what PyPy does, and I'm not an expert, I've actually asked the person I was having lunch with to give a seminar, and he's going to in a month or so, on PyPy, because it's actually quite interesting. But it's written, it's an interpreter, but when it comes across that some instruction that happens very often, or some series of operations that happen very often, it will recognize that, compile it, and swap that in every time that instruction comes up. So that bit will be faster, will become faster as the program runs. So it's very clever. The advantage of writing interpreter in Python, for Python, is that you can do things like, if this list doesn't change very much, then use this very optimized set of machine instructions for it. Okay, or compile it. Whereas if you were writing in C, C doesn't have a concept of a list. In Python, we can create lists very easily, and we will teach you how to do this. So I'm giving you a bit of an overview here. I can say Bob equals okay. And then if I say Bob 4, gives me 2, because the fourth element in a list in Python, by definition, and you have to learn this, is the fourth element is actually the fifth, because we count from 0. So this is the 0th element, the first, the second, the third, and the fourth. Okay, C works the same way as does Java, but some languages do not, like Fortran. Yeah.
Error.
Well, Python is actually quite flexible. It doesn't like to give you errors if it doesn't have to, but this time it does. But you can go things. I'll show you this later. This is later. Bob minus 1, which is from the beginning go backwards.
That's it.
Yeah.
So is that the same as an array in Java?
No, it's different. Yeah, but it's yes. Oh, okay, yes, we will do this later, I promise. This is, we're just giving you an overview. Python can do lists. Don't stress. All right. Really. Okay, I'm giving a bit of an overview. All right, we're not talking about matrices yet, but I'm sure you can look it up. Yes. Okay. So, just so you know that there is this nice idea that you can write the interpreter or compiler program that translates the program that you're writing into machine code. That can be written in the same language that it translates. Okay, and there are advantages to doing that because you can use the expressivity of Python to do some interesting things in the interpreter, some interesting optimizations. So this is stuff I've put there for those of you who feel that you need something else to think about because you've programmed before. All right, I'm not going to examine these slides. I also don't make comments like that on the slides, so it's a good reason to go to lectures. Okay. But when in doubt, study it. Okay. Questions? Yes?
How do you interpret PyPy if it is written in Python? PyPy is written in Python.
Yes.
So what do you use to interpret that to make the interpreter?
Well, you could use CPython, but yes. I'm not sure I understand. I think I maybe eat my coffee. It is an interesting reflexive idea. But once the Python, oh, I see what you mean. How is it? Well, it's going to be running on top of Python itself anyway. Python. It will have been. Good point. I'm not sure I do know the answer to that, but we will have a seminar on it. So save the question for that. I'll take a rain check on that question and come back to it. Okay, so there can be some advantages to writing a compiler in its same language, but the compiler course, for those of you who are feeling that stressed out feeling, is a third year course. Right, we teach you how compilers work. Okay, but it's nice to give you an idea. I'll give you a brief overview. There are lots of different languages. Someone asked me in the last class, what is the best language to be using, or the right language? There is no answer to that. I'm sorry. It's like saying, what language should we be speaking, all of us? Well, you could say English. English, for the reasons most common, but if you're talking about ease of learning, Spanish would probably be a much better option because it's phonetic. You know, there are no, Spanish is spelled the way you say it, whereas English is certainly not spelled the way you say it, and my husband, who's Dutch, is still correct the way he pronounces certain words that he's only ever read. You know. But things like this, like fiel. But, you know, the word you don't do. So, you know, things like that. So there isn't an answer to that. There are just languages that are popular and you have to change all the time. So computer science used to teach Pascal. Then they moved to C in first year. Then C++. We used to teach something called Scheme as well, which is a functional language, which I'll talk about now. And then we moved to Java. And now we're moving to Python. It's dynamic, and you have to see what the lay of the land is and what's easiest, what's best, and it changes all the time. There is no right answer to what's the best ice cream flavor to eat either. Yes? I'm not sure. It depends which community. Are you talking about the gaming industry, or are you talking about science? Actually, Python within physics and maths and the sciences is really taking off. Okay, but I don't know. We'd have to do some kind of heat map, where you see which languages are cited more often on the web. But just because people talk about them doesn't mean that they're using them more. I don't know. It's quite an interesting computer science research topic. Not really, but yeah. Yes. Perl is sort of like Python, but isn't Python. They both begin with P. But no, it's similar. Perl is used a lot in bioinformatics and the life sciences. It does text processing very well. So there are all these languages. Now, when learning, there is proof. The best thing is to learn one thing really well. The jack of all trades, master of none also applies to learning, whether it is physics or programming or cooking. It's better to learn. I know someone gets me talking about baking. Anyway, it is better to learn one thing really, really well and then start learning other things than to try and learn all the languages at once. So the worst thing you can do right now is try and learn a whole lot of different languages. You just get confused. What you need to do is learn Python very well and then see when you want to pick up another language, oh, this is like that in Python. Those things are entirely different. But you do a kind of what they call a mapping. Okay, so it's very hard to learn a lot of languages if you don't understand how one language really works. Okay. Eventually, we expect you to be able to pick up any language, okay, and learn it, and not to have this, Python is the only language. There are a lot of people in science particularly, because they're not necessarily trained computer scientists, but they have to do a lot of programming as part of their field, so engineers, chemists, who will stick to a language because that's the only language they learn. And one of them is called Fortran 77, where 77 refers to the year where it was created. I had to program in Fortran 77 as part of my PhD because all the software was written in that. And there's still a lot of very prevalent software written in Fortran 77. It still works, it just has no new features. It's like people driving a really old car. kind of interesting that they can still do it, but it doesn't have, you know, power steering, for example, or, you know, nice features that make life easier. It will be hard to find parts for it, things like that. But I went to a conference last year in Stockholm, and there was a chap there, engineer, who'd written some very high-end code to run very fast on supercomputers in Fortran 77, because he said it was easier. Which, you know, that's kind of the mindset that I really don't want you to get. Like, you know this language so well, and you're not learning anything else. Damn it, because I've learned this language. It's just not a very flexible way of thinking, and most true computer scientists will not end up being like that. We give you tools, but if you see a better tool for the job, don't just insist on using this tool. So C++, for example, is a great language when you want speed. Python can be 300 times slower than the equivalent C code. C is very powerful, but it's very nuts and bolts, and you very much have to make your own lists and your own arrays and everything you have to do. Whereas in Python it would be one line, it can end up being 20 lines. Okay. So there are all these languages. C# is very popular right now. That's one on my next on my list of things to learn. I don't know C#, but it's apparently very nice to program it as well.
Sorry?
Yes.
You have to say, what are games programmed in? Is that also C++ or?
It depends. You would actually probably have to ask James and Patrick, who are the games people upstairs. But you know, a lot of if you're talking about a game where like sort of hair would be flying around, or you want to simulate water, a lot of that code would be written in C because it's faster. Not even C++, because C++ has object orientation, which adds extra layers. So it depends. But then if you were wanting to rapidly develop a game or prototype it, you wouldn't do that. You would use some kind of scripting language or gaming engine. This is not my area. Yes. You tell me. So what are the implications of the programming language being open source? What does it mean when something's open source? It's free. That's the major thing. You don't have to pay for it. And there'll be a lot of people working on it. What are other implications? Quality is not ensured. They're not that many. Sorry? And that's a very general question. There can be or there cannot be. But we tend to, in academia, go for open source. I know, for example, in my area, which is computational chemistry, there are some programs that are used to do simulation that are free, and others that are open source. And the only people who tend to go, free and others are closed source. The only ones who tend to go for proprietary software are big pharmaceutical companies that can afford it, because we can't afford to pay 500,000 rand a year in licensing, which is what, you know, that's the problem. But then they guarantee support and blah blah. So people who know what they're doing, computer type people, tend to favor open source because we can deal without the support. But when you're a company which wants to make sure that everyone can use the software, then you would go for a more packaged solution. It depends. I like the idea of open source. I'm not sure it always works, but I think the computing community makes it just the types of people involved. Okay. So there are different types of language paradigms. A paradigm, I'm never sure of the meaning of the word actually, but it's like a way of thinking. Okay, so paradigm shift is changing the whole way you think about something. So programming language paradigm really means different types of programming languages in different broad groups. Now the first type are the declarative programming languages. Okay, and that's programming sort of the way I've just been showing you. Each line follows each other line, and you just say what you do. Very straightforward. Fortran, which I mentioned, COBOL, which is still being taught in various places like Cape Tech, just now called CPUT, are declarative, and I've been using Python in a declarative way, just writing instructions. Then we have object-oriented programming languages, which are like imperative languages, except everything is modeled as things called objects, which have data and interact with each other. Some languages force you to be object-oriented. They are object-oriented, and that's all they do, like Java. Okay? Others allow you to be object-oriented. So you can create objects in Python and do it that way, but no one is forcing you to do that. And there are relative advantages to that. You'll learn about object orientation more in 101.6. Sorry, I said imperative, not declarative. I meant imperative languages. I sometimes use the wrong word. It's a bug. I'm not sure it's a feature. So imperative languages, you state explicitly how the problem is to be solved. Object-oriented languages, you phrase everything as an object. Then you have declarative languages, where you say what you want to be solved and what the rules are, and you have a program or the engine that finds a solution. So, do you remember we had the snakes and ladders algorithm? Talking declarative programming, that could be kind of considered an algorithm. It's rules. Okay, but these are interesting languages to know about. They're not used very frequently nowadays. They're very much used in artificial intelligence. Prolog is one of them. And then we have functional languages, which are quite broadly used, where you express everything as a mathematical function. So we do not teach functional languages. Here, we used to, for Scheme. They are very powerful. Not everyone likes them. You tend to have to think a certain way to enjoy programming in functional languages. Mathematica is a very prominent one, but you have to pay for Mathematica quite a lot of money. MATLAB, who's using MATLAB? Yeah, as part of applied maths. That's generally a functional language. Haskell is another one. So that's types of programming languages, and there are lots of them, and there are various reasons to use different ones. I still use awk sometimes. Anyone know what awk is? It's like a sort of little programming language that you can use on Linux that is very useful if you just want to do something like in this text file, just print out the third column. It's like one line at all. So I'll use it for that because I know it's useful and it does. Okay. So ideally you should get to the state where you use the language that suits the task rather than trying to get the task to suit the language. Okay. But Python is very flexible and very nice. Now, just a few slides on software development in general. The old days, the era of the terminal with the big white box in the middle and the keyboard and the mouse was more about, can you do this program? Can I get a program to do this? And now we've shifted into a different paradigm as well. iPad, touch screens, internet is all pervasive, and we're more interested in how do you do it well. So you've written some software. How fast is it? If you have a stock portfolio and you want to buy some stocks and the prices are changing all the time, and you want to see if I bought this spread of stocks, will it make me more money than buying that spread? And you've got various assumptions you're making. That calculation you need to run now. Okay, you can't wait a week for it to finish. It needs to be fast. It needs to be almost real time. Okay, so for some calculations that handle large amounts of data, we really need very fast calculations and very fast computers. How easy is it for others to use? Okay. How easy is it for your average 4-year-old to pick it up and play with it? Or someone who hasn't used computers? A lot of people complain that they don't know computers, they can't even work their cell phone. That's not actually the fault of the person. It's the design of the cell phone. The cell phone is designed, should be designed, so that anyone can use it because it's a phone. It's a basic functionality. If it gets so complicated that people spend ages trying to figure out how it works, then it's lost the plot. And it's the designer's fault, not the poor user on the other end. So software engineers are taking more responsibility for that. How do you design really usable software that's intuitive, that no one needs a manual for? Yeah, you don't want that to be done. And how much do they want to use it? Like Apple's now one of the most valuable companies in the world. It is now, yeah. It's gone $500 a share or something. That's because everyone wants one of those. So this is what we're interested in software development. And some of the aims of modern software development are to do things like build a tool that everyone will use. So the business model for Google, Facebook, Wikipedia when they started out was not some guys who had an idea how to make lots of money. They wanted to build something that was so cool that everyone wanted to use it, and then the business model came. Okay, so I presume most of you have seen that, the Facebook film. Yes?
Yeah.
Social network. Which is kind of interesting. But, you know, Google, Facebook, Wikipedia, those are things that everyone wants to use. And why? Because they're easy and they do something useful that wasn't done before. So that's one of the aims. Another aim is to use very, very big computers to simulate something that hasn't been done before. Something amazing or something very lucrative, like stock portfolios. But Avatar, for example, this is a picture of the render farm that was used to compute the frames in Avatar. It's huge. Blue lines, each one is a server. So everything from Avatar to climate simulations, when you're trying to predict what will be the effect of additional carbon dioxide on the world's climate and project in 10 years' time what's it going to be, those require huge computers, lots of data, lots of simulation to do it. And also to analyze lots of data for interesting or lucrative patterns. Has anyone read Freakonomics? Yeah, it's quite an interesting book. And just by looking at huge volumes of data, even the human genome, trying to figure out which genetic differences cause this disease or give you a predisposition to high blood pressure, that kind of thing. You need lots of data and intelligent algorithms that can sift through that data and find that. So this should hopefully be making some of you excited. With these ideas, I thought it would maybe worthwhile giving some background on who I am and why I talk about the things I do. So I have postgrads and I do some research, but the postgrads do a lot under my direction. That's how research works. Well, it's how business works. You know, they say if you engineer, you do engineering until you get good enough to become a manager, and then you never do any more engineering, because you're managing engineers. So that's kind of how it works in science, so we do try to keep our feet wet. So I'm very interested in high performance computing, really big, really fast computers. Okay, at the moment they're not really big, they're quite small. There's GPU cards, okay, graphics processing units, and trying to use those to do chemical simulations, because I actually have chemistry training. So simulating protein interactions on GPU, this is very important if you want to understand how diseases work, how to get a new drug for AIDS, for example. One of the major ways they do that now is to simulate the interactions and try to understand exactly what's going on in the drug. Because we do not have microscopes that are powerful enough to do that for us, so we build a model of simulation. I'm also very interested in computational science in general, so there's a team of astronomers that we collaborate with who are developing CAT7, NearCat, and the Square Kilometre Array if we get the bid, which is this big telescope in the Karoo, and they have a huge amount of data that's going to come from that, and how to search that data for stars, new stars, how to remove radio frequency interference from that data, which is a new project master student is starting on, things like that. So I'm quite interested in computational science. My own lab and where I do my own research often is molecular modeling of carbohydrates, and I like pretty pictures as well. So we do things like this is algorithm rewrote to display the carbohydrate in a certain way, where the different colored rings means different things. And I have 3 students at the moment working on a very nice system for looking at astronomical data and how to look at really big files of astronomical data which don't fit in memory, but you still want to look at the whole thing. So that's kind of what I do. Any questions? Okay, so now we're going to start on Python at and yes.
I just want to ask, all those slides you just went through, we're not going to write anything on them.
I'm very nervous about saying things like none of this is examinable because people translate that through their own interpreter and they get different things. Okay, and then I get people say, well, you said this would never be in the test, and I actually never said anything like that, well, that's certainly not what I meant. And I will not ask, obviously, on what my research areas are. But, you know, the other stuff, the good way to think about it is how would you set a question on this? I'm not going to ask about how Python, what the Python interpreter is written, that kind of thing. That's, you know, this is really good. But, you know, on computer hardware, those slides are presented, yes, I could ask some questions. Okay. I will mostly focus on the programming and the actual Python. Sorry? There's the textbook to study, and there's VULA. They're the slides I put up, yes. But these are slides I put up. Not all of them are necessarily stuff I'm going to test. But I'm also not that keen on those kind of questions, you know, because the world is an interesting place and not everything is necessarily only worthwhile if it's tested. So, yeah, some of this I think you should just read because it's interesting. I will give you some examples of tests that I've set before. To give you some idea. Okay, so Python is not named after a reptile. It's named after Monty Python's Flying Circus, which is a British comedy sort of group who had a few films and they're quite amusing, so with John Cleese and several others. I presume some of you have seen them? No? And now for something completely different is a line from Monty Python's Flying Circus. The creator Guido van Rossum is now benevolent dictator for life, but Python is actually managed and owned by the Python Software Foundation. Okay, we're using Python version 3, which is rather different to Python version 2, and I'll make that clear. We also are using the integrated development environment IDE called Wingware, and you should have been shown this in orientation. So where is Wing now? Wing is here. All right. There we go. So the other lecture theatre is rather different. On to my screen. Bigger. I don't know why it always works. Okay. So you've had a look at Wing, right? This is where you enter all the commands. I mean, this is a program up here that I've called untitled.py. Okay, I can run it like this. I do try to do programs in class, okay? It's not always the easiest thing to do, okay, to demonstrate something in front of people. You make mistakes and the noise level goes up, you guys will be very good. But if you know, if I'm trying to show you something and the noise goes through the roof, I'll just stop. But I do think that this helps. If you don't think it helps, let me know. But I tend to know from previous student evaluations, you like to see me program as opposed to just talk. But anyway, so what I'm trying to show you here is that this is how we tend to do. We tend to write the commands in a separate file, really. That's what we do when we type here. We save it, and then we run it in the interpreter. This is really the same thing as that little command line interpreter I often use as well. I will use both depending on how I feel. You will get used to it. Okay. Just be aware when I have that other white screen that I am also just doing the same thing as we do. I'm just running the interpreter and doing different things. Yes.
What's the difference between the top part and the bottom?
This is the program that you are writing. It's basically, you could use a text editor. What's the name of a text editor? Text edit for me. Yes. Sorry?
Notepad.
Notepad. You could use Notepad and write it And then when you were on the command line, which in Windows is called CFD, CMD, command. If you're running, you could run it in command. It's been a long time. I retired my last Windows machine 7 years ago. If you run CMD, then you will, I still know it, it's just, in secondary storage. If you run CMD, you can just run the text file program. You'd have to be in the right directory, and you would just say Python and the text file. I can show you how to do that, but not right now. Okay. Just hang on. So they basically are the same thing. This integrated development environment just does it for you. So you write it and then you run it. I can also interact here and write D, and it will say it's 5, and I can say A equals 2, and I can do all of it there if I want to, and then A, that kind of thing, if I want to. Yes. How would you create a graphic interface? We're not teaching that. You basically use a library. You can use VPython. There are various different ones you can use to create a graphical interface. And it's quite easy to do. You just import the library. I'll talk about that later though. But that's later on in the course. Okay. We focus on the problem solving. The graphics is nice to have, but it's just prettiness, really, in the end. Yes. Anything else? Okay. So this is the same as it's basically interacting with the interpreter directly, and you can type over here if you want to. Or you can write commands up there and run it. And the advantage of doing that is I only have to type it once. And if I want to change it, I just have to edit it here. And run. And it will get way more sophisticated than this. At the moment, I'm just doing something very straightforward. Please ask questions. This really is more. I know you're worrying about all that other stuff I told you, and most of it is just background. This is the meat of the course. So we recommend WingWare 1.1 because it's free and it's scaled down and it's very simple. You are welcome to use anything else so long as it works, as long as you can make sure that your program, when submitted, works. The automatic marker every year causes a lot of pain because people are not used to being that precise. If the automatic marker says it's wrong, 99.9999% of the time it is correct, and we haven't made a mistake in setting it up, and you have made it. It is painful, but it teaches you how precise computers are and how precise you have to be. And it's a very good, very fair system. If we had tutors marking your assignments, it's not as even and fair as an automatic marker. So, you can use a separate text editor and interpreter if you wish to do things the hard way. I mean, I can do something like, we have a text editor in Python, in Linux, it's Linux, we call VI. And in VI, I could do something like A equals 4, B equals 6, print A plus B. Have I done anything wrong here? No, it's fine. Okay. And then I would write it. So you write in VI, write test.py. Okay. Now I'm going to exit. Not exit. Okay. So I've written of this file called, test.py. It's sitting in my directory. Okay, this is not how you will do it. I'm just showing you something necessarily. I like text-based interfaces. I think it's I good. I don't really like the stuff so much, unless it's really pretty, like the iPad. And now I can just run it. I can say Python through test.py. Let's hope this works. And then it just says test. Because when I test.py, that's what's inside the file. That's what's in the text file that I created. It just has these lines. And when I run it, it prints A plus B, which is, I think you would agree, 10. So yeah, I'm just saying, that's a Python interpreter. It's a program. Run it and send it test.py. So you can do things that way. I like to do things that way, the hard way sometimes, because I learned it that way. It's easy for me. But it's like someone saying that Fortran 77 was easier. It's not. It's only when you've been doing it for a long time that it is easier. So that's the Python interactive shell, and you can interact with it in Wing, in that little corner box that I showed you, which is over here, if you want to. And it's a nice way to play around. Please play around. You're not going to break anything, I guarantee you. And it also means that you realize what you don't know. You only know what you can't do when you try to do it. Yes. Yes. Runs it with different inputs, not all of which we give you. Okay. So that's why you can think your program's right and the automatic marker thinks it's wrong, because it's tested it with something that we're not telling you about. And it broke. Okay. Okay. So basically what I've just said now is that when you type, you can type commands indirectly, but you lose them and you have to keep on retyping them. So we tend to type them into a file. When you type them in that top box in the Wing, and you save it in a particular directory with the file name, and then when you press run, it does basically what I did there. It does Python and the file behind the scenes for you. So the integrated development environment is meant to make life easier. But in a way, it takes you a step away from what's actually happening. So it does help, I think, for me to show you other ways of doing it. Okay, tomorrow we'll get into a lot more actual Python. You should be happy.